Thank you all for being here. I have no idea who is writing messages on the chat because I can only see my presentation screen. So we'll leave questions to the end, if that's okay with everyone. Not that I can see if it is okay with anyone. But thank you for coming. I'm Patricia Thaine. I'm the co-founder and CEO of Private AI and a PhD candidate at the University of Toronto, focusing on combining natural language processing with homomorphic encryption and numerical analysis. And this talk is going to be about privacy-preserving machine learning, and I'll give you some examples of when to integrate various techniques in a practical sense. So why do we care about privacy-preserving AI in the first place? First, it's pretty clear that the utility of our PII is pervasive. We could find it for all sorts of tasks. That sensitive data is at risk from a number of malicious actors. And as engineers, we want access to data that's usually not accessible to us due to privacy concerns. In addition to that, there's also a financial reason why we care about privacy-preserving AI. And these are the fines imposed over time for the GDPR. Now, there's the CCPA in California to be aware of. There's an equivalent to the GDPR in Brazil that's going to come into effect this year. India is thinking of having a pretty strict privacy regulation. China's going to be requesting that businesses be very careful with personal data. And Canada's considering following suit as well. So this is a really good website if you want to track what kind of fines are being given by the EU and what you should be careful of in particular. So you'll see also that the number of concerns are growing towards apps, browser extensions, software that generally allows you to exchange your privacy for free stuff. So the days of just giving away data for a lot of consumers are over. And you can see that it's also a competitive advantage. So this is the number of downloads for the Signal app. And at the very beginning of last weekend, I believe that's when the protests were, the Signal app download rate increased dramatically. And that's in part because of the protests, and in part because they created a on-device data de-identification module where they blurred faces from pictures automatically, and you could also blur faces from pictures yourself or whatever else you wanted to blur from the image. So that is basically privacy, a visual of how privacy is a competitive advantage, and you can see similar things whenever there's a scandal happening with DuckDuckGo, Brave, Telegram, and so on. So you see spikes during the Hong Kong protests, for example, and so on. And there are a number of AI and machine learning tasks that use potentially sensitive data. So chances are you're going to be working on one that does. And the question is, how can you think about the various privacy issues that you're going to have with respect to the technology that are available? First of all, the key is identifying the 4 pillars of perfectly privacy-preserving machine learning. And then with identifying the pillars, you can place yourself and your problem within these pillars and choose the technology accordingly. So number 1 is training data privacy. And what training data privacy comes down to is preventing the reverse engineering of the training data given an output. So for example, there's a paper by Carlini et al. From 2018, where they show that a character language model will give will more likely predict a secret that was found in a data set, even if that secret was rare. So they give the example of the social security number that was that they'd hid into the Penn Tree Bank, and they used differentially private gradient descent to prevent that secret from being memorized by the model. There's also input data privacy, and what you care about for input data privacy is really preserving the privacy of the user. Then there's model weights privacy. Model weights privacy is for preserving the bread and butter, the IP of the company or organization that created the model. And there's output data privacy, which is once again for preserving the privacy of the user. So let's look at some recent examples. There was a survey that showed that Canadians have conflicting support for COVID-19 tracing apps. And they said 55% of respondents said digital contact tracing should be voluntary, citing privacy concerns and potential abuse of civil liberties. So what we're dealing with here is a concern for input and output privacy. What kind of tools are available to preserve input and output privacy? Traditionally, cryptography is used to preserve the privacy and secure data. And there are two types. Usually they're combined. There's symmetric key encryption, where you use the same key to encrypt and decrypt a document, and asymmetric key encryption, where you use a different key to encrypt and decrypt a document. And more recently, in the last 10 years, there has been homomorphic encryption. And the key thing about the difference between traditional cryptography and homomorphic encryption is that in traditional cryptography, you have to decrypt the data before analyzing it. Within using homomorphic encryption, you do not have to do that. So an example would be there's a data owner who has a public key. They have a couple of messages they want a computation to be performed on by some service provider. So they encrypt those messages, send it to the service provider who does all the processing in the encrypted domain, never looking at the data, sends the encrypted results to the data owner. So the service provider was never able to see what the result was. And the data owner then decrypts the result and is the only one to have seen the input and output. There's also secure multi-party computation that can be used. And this comes down really to having a secret and sharing it amongst various parties, and those pieces of secrets can be used to compute a final result that everybody finds out about at the end without anybody knowing any of the intermediate values or the original values. So this is a very not secure example of secure multi-party computation, just meant to give you the intuition. So this party 1 might add a random number to their message. Party 2 might add their message to that. Party 3 their message to that. Party 4 their message to that. And what all the parties might want to find out is the sum of all messages. So party 1 can remove that random number and send that result to all of the other parties. A third option are secure enclaves or trusted execution environments. And the idea behind trusted execution environments is that you've got a chip, actually, such as the SGX trusted execution environment, which is in a lot of Intel chips, probably in the laptops that you're using. And anything going inside the chip is encrypted. Anything going outside the chip is encrypted. And the processing happens when it's decrypted only inside the chip. And not even the OS/kernel can take a look at what is happening inside that chip. So those three solutions would be good to consider when thinking about how to preserve input and output privacy. In practice, there's a lot of new theoretical work on homomorphic encryption for machine learning, including a group that's working on a private AI project, not my company, separate names, that focuses on combining homomorphic encryption with machine learning. There's also the IDACH competition that includes genomic data analysis. And the interesting thing about healthcare or genomic analysis in homomorphic encryption is that you don't need real-time results. And it is very sensitive data. So it's a really good combination for homomorphic encryption when you have that extreme need for security and don't need the real-time results. For multi-party computation, there has also been genomic analysis done when and some discoveries were made on how to perform genomic diagnoses given genomic data owned by different hospitals. So this is some really cool work to look at if you're interested in that. And there's secure enclaves that are used for facial and fingerprint recognition, for example, by Microsoft for passwordless authentication. So I can, whoever's interested can email me afterwards for these slides. I'm going to go briefly over what this says. But essentially, homomorphic encryption, secure multi-party computation, they can give quantum safe guarantees of security. So they are mathematically provably secure. And what quantum safe means is essentially that we haven't found a quantum algorithm that breaks it, not that we've proven that a quantum computer can't figure out the math behind it. The difference between them and a trusted execution environment, which is a hardware solution, is that we don't have mathematical guarantees for hardware solutions. So it is possible to conduct side channel attacks, for example, or there might be vulnerabilities that we're just simply not aware of yet, as happened a couple of years ago. So if you're, the question, there's a lot of information here, but the question that I get the most is, what's the slowdown? So what's the speed of homomorphic encryption when you combine it with machine learning? And the group from Microsoft managed to get it to the 3 to 4 orders of magnitude slower than computing in plain text. And that's not so bad when you consider that you could parallelize a lot of computations. For secure multi-party computation, the cost is approximately linear in the depth of the circuit, depending on what scheme you use, and the costs grow linearly for communication. And for trusted execution environments, it really depends on the batch size. So there's a very limited amount of room within a secure enclave, and encrypting and decrypting the data takes a lot of computational power in relatively to just computing on plain text data. There's another recent event is that the NHS was under fire for plans to store, track, and trace data for 20 years. And the main concern here is really, how are they going to store the data in addition to why are they storing the data? But suppose the why they're storing the data has a good answer, the how are they going to store the data, how are they going to use the data, how are they going to maintain the training data privacy, because they're probably going to want to train models on this data. Those are the major questions that need to be answered. And one option for this is using differential privacy during the training of a model. So originally, differential privacy was created in order to add noise to the result of a query of a data set in order to allow for generalizations to be made of the data about the data in the data set, and not have specific information about an individual be discoverable. So if there's if you ask a data set how many people smoke and have cancer and have this rare disease, you're going to get an approximate result, and you don't know if the actual answer was 0, 1, 2, or so on. And essentially, you can see this in action in that paper that I mentioned, for example, by Carlini et al., where they applied differentially private stochastic gradient descent to their character language model when learning from the Penn tree bank with that secret embedded in there. And what you're essentially doing is gradient clipping when you're doing differentially private gradient descent. Another option is also uses differential privacy, but in a little bit more of an intuitive way for people who do machine learning. And the way that this is structured is that you've got a student model that wants to learn from incomplete public data. And this incomplete public data has to be labeled. You're not going to label it using a model that was trained on sensitive data, because it might label, its labels might reveal something about the training data. So what you do is you take the sensitive data, you separate it into NIID data sets, and you train a model, n models on each of those sub data sets, and they all have the initial same setting. That the most common result between those models gets sent to an aggregate teacher, and there's a prediction that happens based on that with some differentially private noise added to that, which is often either Laplacian noise or Gaussian noise, depending on your settings. You then use that differentially private prediction to label the incomplete public data and inform the student model when training it. So differential privacy and PATE provide training data privacy. Another option is anonymization or pseudonymization. And what that really means is removing, replacing, or aggregating personal identifiers. And that could be done, and quasi-identifiers. So that could be done in structured data, such as structured medical data sets, or unstructured data, such as text, images, or video. And what that does is it protects training data privacy in a similar way to differential privacy, if you will, because it's removing or replacing the personal data that might contain secrets that you don't want the model memorizing. And it can also, to a certain extent, protect input data privacy. You could still see what's around the personal data, or you could still see some information about the input while still preserving individual privacy. There's also a fourth option, which is data synthesis. And the idea behind data synthesis is that you've got some sensitive data and you want to produce private data that's artificial. Non-private data that's artificial. And one example of this is from this paper that did so with images. And what they did was train a GAN to discriminate between the sensitive data and the data that was generated by the generator to trick the discriminator into thinking that it was the original sensitive data. So there's still a lot of research that has to be done specifically in guaranteeing the privacy of the sensitive data, how much stuff is copied or versus not copied. And there's a company that I'm going to tell you about soon that does this really interestingly. So data synthesis is really providing training data privacy by eliminating the use of the secret data sets. And that basically covers the concern or one of the main concerns of how you're going to maintain training data privacy in this example of the NHS wanting to keep data for 20 years. In practice, differential privacy is used in Apple's QuickType prediction through randomized response. There's also differentially private gradient descent that's used in Google's Gboard. And that is used in combination with federated learning and secure multi-party computation. So federated learning is being talked about a lot, which is an awesome way of, one, making your training of your models cost less, because you don't have to do it on the cloud. You could give it to other people's devices to do. But if you don't do it in combination with differential privacy and secure multi-party computation, you're not guaranteeing as much privacy as you could. So you could still reverse engineer what the inputs were by the model weight updates, for example, that get sent up to the cloud for aggregation, if you don't combine it with differential privacy and secure multi-party computation. For anonymization, pseudonymization, it's often used to identify clinical data sets, for example, that are shared with researchers, such as the I2B2 challenges. And for data synthesis, Replica Analytics is one of the companies that I know of that creates synthetic structured healthcare data. They are a Canadian company based in Ottawa, founded by a professor at the University of Ottawa called Khaled El-Imam. So really what you're getting with differentially private gradient descent and PATE are mathematical guarantees of privacy based on the amount of noise one inserts. With anonymization, pseudonymization, and data synthesis, what you're getting are not mathematical guarantees of privacy, but you are getting, you should combine them with strong re-identification risk metrics that are based on combinatorial analysis. So it's really key to be able to do those risk metrics properly. Otherwise, you end up with the headlines that say, such and such data set re-identified, anonymization doesn't work, woe to everybody who uses it. But really, if you use it properly, the chances of you getting re-identified are very, very low, even about as low as re-identification with differential privacy. Some final points is that we can protect users' private data while continuing to use them for AI and machine learning in general. And you have to have a very clear understanding of the problem you're trying to solve before deciding which privacy-preserving method to use. And there's lots of room for research and innovation in privacy-preserving AI. What we're doing in particular at the University of Toronto with my advisor, Gerald Penn, is that we're combining privacy-preserving methods with numerical analysis and natural language processing in order to optimize the NLP algorithms to these various tools. And at Private AI, what we're doing is we're making it really easy for developers to integrate anonymization tools at the edge, so directly within iPhone, directly within Android, directly within browser, or even on-premise, where you separate personal data like names, locations, organizations from text, and you separate faces, license plate numbers, personally identifiable text from images and video. So I'm going to leave you with another problem for you to think about how to solve. There's been a lot of talk about using thermal cameras for detecting whether or not somebody has a fever. And what that ends up leading to is something that I don't hear discussed much, but input and output privacy of the people who are being filmed. And this is interesting because thermal cameras are actually more robust for facial recognition than traditional cameras. Of course, you do have to have an image that's somewhat equivalent, maybe, to be able to re-identify somebody properly, but that's something one can acquire. And the reason that it's more robust is that you don't have the effects of shadows that you have in traditional cameras. You don't have a problem with it being dark outside, so you can't see the person's face. And you could get additional information such as the blood vessels or the facial vascular network that might be traceable from and unique from one person to another. So feel free to to follow us on Twitter. I'm me on LinkedIn, or look at our blog if you're interested in reading more about privacy-preserving tech in general. We have an intro to homomorphic encryption there, and some stuff about privacy-preserving natural language processing. So I will take questions. Do you have any advice for early-stage startups to think about privacy right off the bat, and not as a nice-to-have after securing revenue funding? What easy, cheap, open-source solutions are available? I love that question. Okay, so it is very important for an early-stage startup to think about privacy right off the bat. Not only because privacy by design is integrated into the GDPR and a requirement for you not to get fined, but also because it will ensure that you don't have a scandal that destroys your company. So in part, some scandals, some large companies can take large scandals, whereas small companies can die very easily from them. So thank you for your question, Krish. There are certain tools. There's OpenMind that I think is working towards deployment ready, being a deployment ready library for federated learning combined with secure multi-party computation for, I believe it's for aggregating the weights, but I'm not sure. There's TensorFlow privacy for differential privacy integrated into gradient descent. There's PyTorch that also has differentially private gradient descent integrated. And I have a blog post that talks about perfectly privacy preserving AI. And at the bottom, I have a bunch of resources that you could look at. So thinking about privacy right off the bat is difficult because there aren't a lot of resources out there to guide you through them. So I'm happy to discuss that with you if you message me. I can go through some ideas with you. Hopefully that answers your question, sort of. Any other questions? Okay. Oh, there are some more questions? Oh, sorry. Thank you. Oh, there are a lot of questions. Okay. Did I say India? Yes, India is integrating a privacy regulation, it seems. So Canada, I think India is more ahead than Canada with regards to determining what it's going to integrate into the privacy regulation, but I don't think it's official yet. Any special advice for biomedical data sets? Okay, so special advice for biomedical data sets that could potentially contain patient data. And for opening it to basic science researchers. So I2B2 pseudonymizes the data. So that could be one option. It depends, is it structured or unstructured data, Al? Structured. Okay. So for structured, you could either use limited queries for that you provide the answers to for the research community. And use differential privacy there, or you can look at, so can you hire a company for this, or is this something you want to do internally? Okay, so there are a few companies that do this very well, including Privacy Analytics, for aggregating the data in such a way that they use very strong re-identification risk metrics and ensure that it's HIPAA compliant de-identification. And otherwise, it's kind of risky to do that on your own, but make sure you have strong de-identification metrics if you do it on your own. Happy to go over some with you if you'd like. Let's see, other question. Can you use homomorphic encryption for non-deep learning approaches like just a plain linear model? Yes, absolutely. Yeah, so you can, it's faster for just a plain linear model. You could use it for anything that requires polynomial operations. You just have to avoid non-polynomial operations, which makes it complicated for using it for deep learning when you have ReLUs and sigmoids, but there are some ways around it, but it's still a research question how to do it efficiently for all cases. Any other questions? What was the title of the paper I mentioned? Krish, which paper? Oh, sorry, not Krish, Kamya. Yeah, I'm not quite sure which paper that might have been, but message me afterwards. We could figure it out. For differential, Carlini 2018. Let me look that up very quickly. It's in. Okay, message me and we'll figure it out. For differential privacy, is there a hyperparameter to add a quantity of noise, and how do we decide the optimal value? Yeah, so deciding the optimal value is still somewhat a research question. Some research papers might give a little bit of guidance towards, and I'm happy to point you to some. There is an epsilon and in some cases a delta, and the epsilon was the original value that you saw that gives, you add it to determine what the likelihood is of the same result occurring given, to a query occurring given one modification or one added person or one person less in a data set, for example. And later a delta was added in order to give a little bit more leeway. So it's still, that's a pretty complicated question, but I'm also happy to point you to papers if you message me. Has there been a demonstrated vision test like object detection, segmentation, any good reference to look at? Has what been demonstrated for vision tasks like object detection and segmentation? Andrew? Okay. Homomorphic encryption, differential privacy for object detection and segmentation. I can send you some references They're for object detection. I've seen some for authorship identification. Sorry, for speaker identification, not authorship identification, and for facial recognition. I haven't seen any for object detection specifically, other than through of MNIST. So I guess there's some MNIST papers I could send your way if you're interested. Yeah, so there are challenges with non-polynomial operations, non-linearities. And the way that that's solved is either through approximation, through replacing certain functions like ReLU with an x squared function. Instead, you could also, there are these polynomials called Chebyshev polynomials that are orthogonal to one another, where you can multiply to make it kind of look like a sigmoid function. But the issue is that it gives probabilities above 1 and below 0. So it's not, it gives results above 1 and below 0. So you can't really use it for probability distributions. But there are ways to go around it. But using homomorphic encryption for tasks really requires a lot of numerical analysis more than anything. What are your expectations for how customer information is utilized in marketing tech? What change is coming to the industry? So that's actually something we're looking at with private AI. There isn't that much research on it so far, but if you message me, I could keep you posted on what kind of things we discover. Cool, send me a message. What about performance hits by adding noise? That's also something that you have to determine using some numerical analysis, which is basically just running a bunch of experiments to see what it does on a task-by-task basis. It's just time-consuming, not particularly difficult. Newbie to ML, how does transfer learning work in privacy preserving? Is it possible? Yes, it is possible. So it depends what method you're using, I guess, for answering how transfer learning works for privacy preserving machine learning. But essentially, you can use differentially private gradient descent for training a model on one data set and then continue to train it on another data set. That's perfectly doable. What you're learning are generalizations. So in some cases, it actually makes the model more robust because you're not learning specifics to a particular individual. But if you have anything in mind in particular, Blair, please feel free to reach out. What are your thoughts on common privacy constraints in addition to PII information for the education domain? So for the education domain, do you mean specifically looking at what people do with the data from online classes, for example? Okay, so that really comes down, so if we look at the GDPR, what it says is for anything that you're using somebody's personal information for, you need positive consent for it, no matter, and you can't just keep data eternally. You have to use it for what you need and then get rid of it. You also have to answer to access to information requests, requests for deletion, and there is a really nice infrastructure in the GDPR that can answer how to deal with education domain data and should be generalized to all personal data, really. So it's really about dependent on the company and what their privacy policy says. Ideally, their privacy policy doesn't say we're going to send this to third parties and use it for stuff. Okay, what about performance hits adding noise? There are some papers analyzing that for certain tasks. Happy to send them to you if you have a task in particular in mind that might be relevant. In some cases, so there is one issue with differentially private gradient descent is that you have to balance this noise with performance hits. If you get a really good balance, you can even increase accuracy, but that's not the case for all tasks. Thank you, Shady. Any other questions? Thank you. If anyone wants the slides, I'm happy to send them your way. Just send me an email or something. Or cool. Oh, thanks. My pleasure, everybody. Thanks for being a great audience. All right. So if there are no more questions, I'm gonna log off. But like I said, do feel free to send me messages. And oh, thank you guys. I'm so glad you liked it. Really appreciate it. Have a good night.